Hello, I'm Mr. Franklin. Today we're going to talk about light. First thing you need to know about light is a more correct name for it would be electromagnetic radiation. And partly that's because when we think of light, we usually think of the visible spectrum of light, and way back in kindergarten you even learned Roy G. Biv. Those are the colors of the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet. But light is made of more than just the colors we see. It also includes radio waves, infrared waves, ultraviolet, that's how you get suntan, sunburn, X-rays, for when you break an arm, or gamma rays. The gamma rays are used in things like the gamma knife to treat cancer. They're also what's used in comic books that created the Hulk, okay? Gamma rays. Now all of these come in the form of waves. So let's look right here for a second. If you're writing this in your notebook, you're going to want to leave this space here, but let's talk about waves real quickly. Okay? So waves in general are anything that has a pattern or oscillates back and forth. Okay? So in this case, we think of water, ocean waves, right? But well, light actually travels in a wave as well. Just as a review, this letter right here is the Greek letter known as lambda, L-A-M-B-D-A, lambda, okay? It's basically an upside down Y, or you can make a squiggly L and then add a little kickstand to it, okay? Greek letter lambda, and it basically is a measurement of what's the distance of one wave in meters. So lambda, upside down Y, it's the length of one wave in meters. A lot of times early on in your education you've probably heard crest to crest, but if you trace the path, where does it start over? It starts over right here. Well, that's where one wave occurs. In higher level math, you usually start at the origin, right? So we start here and we go, where does the wave repeat? It starts to repeat there. Okay? You can also go trough to trough, so we could go from here to here. On this particular type of wave, that distance from here to here, from here to here, from here to here should be the same no matter what. Okay? This right here is the Greek letter nu, N-U. Basically, it's like a V, but you put an extra tail on it, okay? Almost like horns, okay? It's getting ready for the charge. So that's nu. And what it says is how many waves happen in 1 second. So in 1 second, how many waves, how many times does it repeat itself? And the units for that are cycles per second, also known as the hertz. Not I hurt my hand, it is hertz. H-E-R-T-Z. Sorry about my writing there. Hertz. Okay? Now, just like we've been learning in class, King Henry died while drinking chocolate milk, missing no pinkies Friday afternoon. Okay? Base unit, we've already learned that's where meters goes, right? Guess what? Hertz also goes there. So we can have kilohertz. Hear that on the radio, okay? Your radio is tuned to kilohertz. So 101.9 kilohertz on your radio dial is 101, here let's write it, 101.9 kilohertz. How many hertz is that? Kilo, 1, 2, 3, 1, 2, 3. So 101,900 hertz, or 101,900 cycles, waves every second. Okay? It's going pretty fast. So that's what hertz tell us, is how many cycles, how many waves are happening in 1 second. Okay. Keep those in mind, and now we're going to talk about how do these fit in with these different colors of light. Okay? So, first off, let's talk about energy. We're talking about Bohr's atom, and we're going to be learning that delta E equals this constant times frequency. But energy in general for these guys is small here and very large here. So as we go this way, it gets bigger. So which one has the most energy? Gamma rays. Okay? So if this gets bigger going this way, frequency, if this number never changes, what has to happen for frequency? If this number is always the same and this is always getting bigger going this way, that means the frequency is slow or small and it has to get faster or higher number. But if you think faster, it's got more cycles per second. Okay? So it's going faster. Wavelength. We haven't learned this equation yet, but the speed of light equals frequency times wavelength. If the speed of light never changes, and this one's getting bigger, then what does this one have to do? This one has to get smaller. So this one has large distances. And actually, if you think in radio terms, high frequency radio, which is the slowest of all of them, has wavelengths large enough that it can bounce off the atmosphere and travel around the world. As opposed to your FM radio station, it can only go several hundred miles. Okay, it can only go a certain distance. So, but anyway, the wavelength here is large, covers great big distances, and the wavelength here is small. And if you've ever done this, if you've ever gotten a jump rope or like a water hose, and you have your buddy hold the other end and you're making the waves, as you make the waves harder, you get more waves, right? You get a bunch more waves, but what do? They get smaller and smaller. Okay? So that's what's happening. As you add more energy, you get bigger energy. The waves start going faster, so you have more of them. You have a bunch more. But the size of the wave is getting smaller. So you get more waves, and they're going faster, okay, as far as how many cycles, how many waves per second, but their size gets smaller. Okay? And this can be confusing, but we got to say the speed of light, how fast these waves travel, like your car, how fast your car travels across the ground, the speed of light is the same for every one of those. But the radio wave travels just as fast as the X-ray wave. They travel the same speed, not to be confused with frequency, which is how many waves, how many bumps you get in 1 second. Okay, so don't confuse those two.